All right, so hello, this is Chemistry Day 26, and this is discussion 2. This is what we're going to go over during class today, potential energy diagrams of reactions. Hopefully you found this document. Some of it is the same as what's in your paper packet, but there's an extra piece in this document, so you might want to look at that. Okay, the video, hopefully you clicked here to find it. Okay, so we're going to take a look at these graphs of what happens during a reaction. All right, so each set of reactants or products contains some amount of energy stored in the bonds of those elements that are stuck together, right? So kind of like, almost like they're stuck together like with little springs. If you remember from physics, they, springs, whether they're stretched or compressed, can store like different amounts of energy. It's similar to the bonds in an element, right? Or in a compound. So if you have like, let's say CO2, right? You have different amounts of energy stored in the bonds that connect the carbon to the oxygen and then the carbon to the oxygen on the other side. So each set of reactants or products contains a certain amount of energy sort of stored already, okay? So that would be, in this case, this level for reactants, okay? And then afterwards, those same elements, when they're rearranged, contain a certain amount of energy, okay? Same in this kind of reaction B, which we'll label in a minute, the reactants have a certain amount of energy, and then after reacting, they have less energy, all right? So this is how you're going to determine if the reaction is overall endothermic or exothermic, okay? So in this case, this is the energy of the reactants, all right? This amount from here all the way to the top is what is called EA, okay, or the activation energy. Okay, and we'll define these in that chart in a minute, but the activation energy is basically the amount of energy that you need to put in order to break all those bonds apart, okay? So like if I have like, say I had like something like this plus something like this, right? I would have to put in a certain amount of energy here to kind of rip these apart. I'd have to put in this much energy, and then when they came up here, it's like they would all be sort of separated, right? You're gonna have to put in a certain amount of energy to pull these compounds apart into their individual elements, okay? And then maybe they're gonna come back together, right? And then maybe afterwards they look like this or something. I don't know, this is just made up, right? Okay, so they're gonna come together in a different arrangement than they did before. And so now these products store a different amount of energy than they stored in the beginning. Okay, so that's what we're trying to look at. Okay, so this distance here, the difference between the reactants and the products is what we call delta H. All right, and that means basically that's how you're going to be able to tell if the reaction is endothermic or exothermic. Okay, we'll get to there in a minute. Okay, so same thing over here. Let's say you have a certain amount of reactants, and let's say, I don't know, it looks like this, and then maybe there's like, this or something, right? Whatever. Okay, these reactants, when these elements are arranged in this way, they would store a certain amount of energy. Okay, then I would have to add in from here up to here this much energy in order to break them all apart. Okay, right? So I'm going to have to add in a certain amount of energy to pull those apart, just like breaking apart magnets, right? Like if you think if they're all connected by magnets, you'd have to put energy in to kind of pull those apart, okay? When they form back together, right? Let's say maybe now they form, I don't know, something like this afterwards, right? This arrangement of elements stores less energy than it did originally, okay? So this delta H is still the difference here, right? Between the reactants and the products. Okay, so if you have, this is how you'll be able to tell if it's overall endothermic or exothermic, okay? So all reactions really have parts that are endothermic and parts that are exothermic, right? You always have to add energy in endothermically to break them apart, okay? And then energy is always released when they come back together, all right? So it just depends kind of which one wins out, okay? So in this reaction, I had to put a lot in, and then I only took that much out. So this one is going to be net endothermic, right? Because overall, I had to put in more. I had to put in more here, right, than I got out. Okay, the products are more energetic than the reactions, right? We've had a net positive gain in energy. So that means it was endothermic. Okay, in an exothermic reaction, there's not as much energy required to break everybody apart. So it has a small endo piece, but then from here all the way down to here, it's releasing a lot of energy. Okay, so this one's going to have a negative delta H, which is going to make it net exothermic. All right, so coming into the reaction, you're always putting in energy. You're always getting energy back as those elements reform. All right, whichever one ends up winning determines whether it's overall endothermic or this one is exothermic. Okay, good. All right, so let's look at those little chart. Oh, why is this kind of, let me see if I can move this. Oh, I can't stand teaching online. This is awful. Let's see if I move it like this. There we go. Okay. Okay, let's see. All right. Okay, so let's just kind of fill this out. I'm just going to go ahead and write it in here, I guess. Let's try another color, just for fun. I don't know what's wrong with this pencil. Okay, so chemical potential energy, we could sort of just define as the energy stored in the bonds of the compounds, I guess, let's say. Okay, sort of the arrangement of the atoms, right? So every arrangement of atoms, like whether it's, you know, 2 carbons or 2 oxygens and a carbon, or whether it's like a sodium and a chloride, or, you know, a water, right? Whatever. Each arrangement of a compound stores a certain amount of energy in its bonds, kind of like little springs or magnets. Okay, PE of the reactants, right? That's how much energy stored in the reactants altogether. Oops, in reactants altogether. Okay, and that's like that first flat line on the graph, right? And then the energy stored in the products is the second line on the graph, right? And that is how much energy is stored in the products. Okay, right? Because it's going to be a different amount because those elements have rearranged their atoms to be different and have different bonding structures and different arrangements. So they're going to store a different amount of energy. Okay, that EA is what we call the activation energy. Okay, and that's the energy that must be input to make the reaction go, basically, to break the compounds apart. Right, to actually make the reaction go, to break those compounds apart into their elements so they can reform in the reaction. Okay, all right, and then delta H is the overall energy loss or gain in the reaction. I'm going to label reaction RXN, okay? All right, so if it's a positive delta H, it's endo, and if it's a negative delta H, it's exo, right? So positive delta H would mean I put in more than I got back. A negative delta H would mean I got out more than I put in originally. Okay, that's going to make it a negative delta H, okay? All right. Okay, now you're going to go back to this document. Okay, fill that out. Now I want you to work through this simulation. Okay, I'm going to kind of start you on it, but then I'm not going to answer it for you. I want you to work through it. All right, and then you're going to answer all these questions. I'll probably put up a key, I guess, but please do it first. Don't just copy it because then you're going to be lost. Okay, and then you can do some practice work here. Okay, based on this graph. You're going to label a couple things, and you're going to look at the differences between the endo and exo and the difference in the amount of energies. Okay, so mainly what you need to be able to get out of this, right, is when I look at these graphs, I need to recognize which graph is endo. Okay, that's the one where the products have more energy. Recognize the graph that is exo right there. Okay, for homework, I'll help you through the simulation in a minute, but for homework, if you have the packet, if you had the paper copy, it's just practice 2 in there. If not, there's a document with it. And it's pretty simple. You're just going to do it, but it's just going to be a little bit more quantitative, right? So you're going to label this axis here with the energy. Oh, I should probably show you one of those, huh? You can probably figure it out, I think. Okay, this you're going to label with the energy, and then you're going to be making the graph that looks like, I can't draw it on here, that looks like, you know, flat, around, blah, or whatever, just like the graphs we just drew. Okay, and then you're going to calculate the delta H. Okay, and then you're going to see if it's endo or exothermic. Okay, and I think you can probably figure that out. I'm going to let you figure that. There's only 3 of them, and then this little one. Okay, so the homework's pretty easy. Okay, all right, back real quick to the simulation. So if you look back into the day 26 document, you're going to go here to this link for the simulation. It should look kind of like this. Okay, so basically all you're going to do is there's an exothermic or an endothermic tab. You can see the way the graphs look different. You see exothermic ends lower, endothermic ends higher. And then you're basically just going to click through this, break the bonds, kind of watch what happens, whatever, answer the questions. Okay, it should be pretty simple, I think. I'll go ahead and post a answer key for that a little bit later, maybe the next day. Oh no, it's due on Monday. Maybe sometime, Tuesday, maybe sometime if I can get it done. Okay, and then finish that, and then I'm going to have office hours, which is your today, hopefully when you're watching this, which is Tuesday. I think I said 2:30 to 3:30. I have to look, but look in the calendar, there's a link. Okay, all right, and as always, let me know, please, if you have questions. Bye.